So yesterday we discussed about how to use the tools. I demonstrated both Vivado as well. We also looked into like internal architecture of FPGA, how actually an RTL design mapped into FPGA, right? And also we had seen like various steps. We started from a simple RTL design, then we synthesized, we converted into lookup tables, and then we mapped into each components of these FPGAs. Each LUTs or CLBs. And one thing you have to remember, whenever you actually look into Altera-based FPGA or Xilinx-based FPGA, so some of the terms may vary. Here whenever we say lookup table in Xilinx-based FPGAs, so in Altera-based FPGA they refer it as logic elements. Here in Xilinx-based FPGA we usually say uh, block RAMs, whereas in Altera-based FPGA we usually say M9K blocks or memory blocks. So slight terminologies may vary, and some of the attributes may vary, but the idea behind both the technologies are same. If you use like one of the devices, then you can easily uh, use another device as well. Doesn't matter like whether it's Altera, whether it is Xilinx, or like nowadays like Lattice, Microsemi, and even like Acronic has come up with their own FPGAs. Having said that, yesterday I made one statement that even though we spend around like 30% of the time in design, rest of the 70% for the debug, right? And in that 70%, most of the time we will be revolving around timing issues. Okay, so if you, as a FPGA engineer, right? So in my interviews, most of the interviews, what I take, I check for the timing because writing RTL and uh, writing RTL, designing in FPGA, that like once you are familiar with that, like anybody can do that. But you want a design, like a complex design, fitting into that small FPGA by meeting the timing is the critical, right? So each time we hear from the people that my design is working fine in the simulation, it is not working in the hardware, right? That is mainly because of the timing aspect. So meeting the timing is critical thing. And if you see in the VLSI industry, for the timing resolution and timing fixing itself, there is separate role, right? We call it as static timing analyzers or like STA engineer. So timing is the critical. So today we will mostly discuss on the timing aspect of FPGA. Initially, I will discuss some of the aspects like what we will be going through, what are the methodologies we all this timing, right? So I'll also demonstrate that like how actually like when how in what scenario that timing occurs, right? So what is the impact on the FPGA design? So all these aspects, let's see. Let me present my screen. Hope this screen is visible to you all.
Yes, sir.
Yes. Yes. So before getting into this particular slide, so I want to understand from your end what you know about timing. I mean, when do you say that like your timing is not meeting? In what scenario you say that like timing is not meeting? And what is the reason behind that timing issue occurs? You all heard about various terminologies about timing, right? Can you tell me some of the terminologies? What terminologies you have heard in terms of violation? You might have heard about setup time, hold time, skew, right? Jitter, lot of terminologies. But why that actually? What is the significance in any digital design? I would like to be this session to be like actually interactive, so that like I can understand like whether you are getting what I'm trying to say. So, what is the importance of timing? You can unmute and tell me the answers. Yes, one of the thing like as Sujata madam is saying, maybe more propagation delay of the combination. Yes, one of the main reason behind is due to propagation delay. There are various other factors, but like main reason is propagation. Any other points?
To reduce time delays, sir, between
Yes. Hmm. Speed of the, I mean, basically it impacts the
yes.
speed, right? So yeah, external noise also impacts. True. I mean, jitter, skew, and external noise. External noise, ideally, like it causes some kind of jitter. Uh, that again, like we have to clean it with the PLLs. Yeah. So basically, whenever I say a timing issue, right? So we encounter whenever there is a timing issue, we encounter some unknown state, right? I mean, in the data part, we will be encountering some kind of unknown data, mainly due to timing violation. We will see that like how that occurs, that unknown state, or like how that unknown state is created, right? So we usually call it as metastability state, right? So whenever actually like I go for the timing analysis, one thing what I have to do is like I have to avoid this metastability by appropriate methodologies. Okay. One is analysis part, we say static timing analysis. So dynamic timing analysis also is available. This is static timing analysis, right? It's not a dynamic timing analysis. Dynamic timing analysis usually using simulation, like we see that like how it behaves. So in terms of performance also, we have to optimize. Whenever I say that like I have a setup violation, so the general way how I can do it, like if I reduce the clock speed, my setup violation is going to be solved. But again, the reducing clock is not a solution, right? Let's say like if my clock is operating at 100 megahertz and you see the setup violation, one obvious methodology what people think is like reducing the clock, because my design is not meeting that particular speed, so the people will start reducing but that is directly impacting your clock speed or what you can say performance. But that is the not right methodology. Instead of reducing the speed, with what method I can improve the performance? That is the methodology we use it in the timing resolution. So that we will discuss like how to solve this setup violation, hold violation, with what methodology we follow, so that like performance will not be compromised. Uh, like let's say I'm operating my FPGA at 200 megahertz. Uh, by changing my clock frequency to 100 megahertz, definitely this setup violation will go, right? But that is like that purpose is not served. I mean, I reduce the performance, right? I have to keep the 200 megahertz as is. In the architecture, I have to modify such a way that this setup violation will be resolved. So that is my objective. Okay, how we do it, that we have to understand. Okay. So especially in the low speed design, let's say like if you are designing some kind of small drivers, let's say like some motor drivers or a simple low speed drivers, right? In that scenario, this timing violation doesn't, occur much. You will not see that kind of timing violation, mainly due to the speed. This is like, especially in the high speed design field, that thing. Okay. So, and especially in the MPSoC kind of design, which is meant for high speed. So, if you have like smaller design, which is consuming some 10,000, LUTs, so easily will not see this timing violation. But as the number of lookup tables in your design keeps on increasing, as your complexity of the design goes higher and higher, so you start seeing these kind of setup and hold violation, and that has to be resolved properly. So first thing is like quickly I'll go through the basics. So you might all know the fundamentals of what is setup and hold. But just to recap, what exactly the setup and hold. I'll take one simple example. I have two flip flop. I'll simplify as much as possible so that like you'll have a quick understanding of the basics. So this is my data from flip-flop 1, what I'm transmitting. Okay. So this is my clock. So I transmit the data from this flip-flop. So this is launch flip-flop, right? And I can say L1 launch flip-flop. So here L2 is the latch flip-flop. So this flip-flop 2. So my data has to travel from flip-flop 1 to flip-flop 2. But ideally, whenever actually transmitting this from flip-flop 1 to flip-flop 2, it is not a direct path, right? So there will be some combinational logic, combinational logic. And then it goes to flip-flop 2. This is the ideal path, what usually we will be having. Now, the scenario is at this rising edge, like the clock, let me consider this is the clock. And at this point, that is this rising edge, I send some data. Okay. This is here I send the data. So let me consider this as the clock period, that is T. Okay. So now the scenario is if I launch the data at D, right? So usually like in the sequential design, how this data will be propagated. So at this rising edge, the data is launched from here, and at this rising edge, data will be captured at flip-flop 2, right? So ideally, what is the assumption is, so here, let's say like data is there, like this point, maybe I can say Q1. At Q1, data is launched, right? So here in Q2, at this point, if this is the data, like let's say this is the data which is launched at Q1. So this delay, right? Whatever the delay we have, this should be minimal enough, such a way that here that data should be there, correct? To launch it. There is a propagation delay. I can say TP. Let's say after TP, at Q2, I should get the data so that this edge can be latched, right? But if this TP is like higher, higher than like let's say that may go somewhere here, right? So when this rising edge, it will not see that data, right? It will miss to see this particular data. But again, it doesn't mean that like we have to get data at here itself, right? Uh, Often, like I give a analogy of a railway station or like your airport. So even though flight is departing at like let's say 7 a.m. or like 8 a.m. So it doesn't mean that like you have to reach airport at 8 a.m. right? You have to be little before that, maybe like 1 hour before that, right? Like say 7 a.m. you have to be there at the airport at 6 a.m. So the setup time is like that. So this data it expects somewhere like before this. We call it as T setup. Okay. So whatever the data is there, right? By T setup, it should be ready. Okay. So here, like this gap, whatever we have from the rising edge of the clock, slightly before the date, slightly before the rising edge of the data should be ready. Now, my whatever the propagation delay, or I can say this whole delay, like usually the delay will be from this point to this point, and from here to here, right? So that plus T setup. Okay, I can say T clock to Q1 plus T propagation plus my T setup, this part. Okay, T setup. That should be less than the clock period. Okay, then I can say my setup time is met. Okay, so if it is not meeting this particular condition, what will happen? I'm going somewhere here. My data might fall here, or my data might fall here. I'm missing to observe that data. I'm not seeing that data properly, right? That is the main cause of setup violation, right?
Sorry to disturb you, sir. Sir, can
Uh,
you please take whiteboard instead of black? I think it will be more effective. We'll be able to make out where you are.
sure, madam. Sure. Let me change the background. Okay. So this is this clear so far? I mean, I'll just change the background. So, but like so far, is it clear? Any questions?
Yes, sir, it was really clear. It was.
Okay. I hope this is clear. I mean, this is fine, right?
Thank you, sir.
Yeah, no problem. Yes. So here, hope this setup violation thing is clear. So now, what could be the possible resolution for how I can solve this setup violation? How I can solve this? So this is a clear. I mean, you can clearly see this like this how the setup violation affects, right? So how I can solve this? What is the possible methodology for this? Yes, we need to reduce the TP, right? One is reducing the TP itself. Usually another method that I mean people I mean that is also true. I mean that is how actually we analyze the optimizations or my maximum clock at which the design can be operated. So that is the one thing like we call it as critical path. So usually like we can reduce the clock. That is also valid method. I understand. I mean, but it compromises with the performance. Let's say like if I reduce this T itself, if I increase this T itself, basically when I say I'm increasing this T, uh, what happens? It actually uh, what happens actually? If I decrease the frequency, it means actually I'm increasing the T, right? So I mean that is one reducing the T, right? So that is one option what I have. Like with the lower frequency, I cannot. But the issue is I'm compromising with the performance itself, right? Uh, so then what else I can use? So the either other way is basically to split this combinational logic. Either like uh, when I say that like I mean split this combinational logic, one way is like you can completely re-architecture your combinational logic, right? So you can go with some parallel architecture, whatever the congested combinational path is there, right? So that you can go with some parallel architecture and then you can. But the main methodology, I mean, the popular methodology, what I use is pipeline, pipeline, right? So in pipelining, what I'm going to do is this huge combinational path, I will split into C1 and C2. And in between, I will put one flip flop. Okay. So now this TP is reduced, right? I mean, it is a reduced one, TP1 and TP2. That is the reduced delay, correct? So now my combinational, I mean, my setup and hold violation, that is with respect to these two flip flops. I mean, here to here I analyze and here to here I analyze flip flop 1 and flip flop 2. This analysis is made simpler, or like I can say it split across multiple flips, right? So this is the pipelined way of implementation, right? Now this whole setup violation is actually resolved. I mean, again, it may not be resolved with one stage of pipelining also. You may have to go for multiple stage of pipe. But here, one more issue we introduced. What is that issue? Here, even though we improved the setup violation, what is the another issue introduced here? Another challenge is introduced. I cannot say that issue. Basically, we are introducing the latency, right? So the common mistake what we do, like we go for pipelining. So usually this path, like I mean, this can be like some other path also is there. That path was coming in a particular. I mean, you have aligned both the path, like path one and path two, and somewhere you are adding these two data. Now, if you properly don't match the pipelining stages in the another path, then you're going to get the wrong result. So you have to balance the pipelining properly. Okay, that is a very important thing. And you are introducing the latency also. Previously, you were expecting this output to be at after first clock, right? One clock cycle. Now the latency became two clock cycles. This is a trickier thing. Like I mean, you have to carefully handle. But this latency is during startup point, right? I mean, whenever you actually start the thing, like let's say like you have an FFT Once you start getting the data, from that latency onwards, like you keep getting the data, right? So it is like continuous propagation. So, but this is only during first clock cycle you will see this kind of delay. Okay. Hope this is clear. So this is the methodology how you can solve. But there are actually many misunderstanding with respect to FPGA. That like whenever I ask people how to solve the setup for hold violation in the FPGA, so the usual answer will be like I will put a false path constraint. I'm going to put some multi-cycle path constraint, or they say I'm going to put some delay constraint. So constraints are not solving the violation. Okay. Constraints are something that I'm informing the tool that this is a false path. What is the meaning of false path? It is something like don't consider this particular path for the analysis. So it is you are explicitly saying, I know there is a timing violation in this path and don't analyze it. So like usually I like when I consult these startups for their like design reviews and all. So I usually see that like there is no timing violation and simulation is working fine. When they put it on board, it is not working. Then I have to keep debugging that what kind of constraints they put. So they wherever they see the timing violation, they keep putting the false path or multi-cycle path. By default, tool will ignore that path and it doesn't analyze the timing, and it is showing that like timing path, timing clean, positive, high, positive, slack. So, but when I keep reducing all these constraints, right, I start seeing the timing violation. So, the false path and multi-cycle path, these kind of constraints you have to put at the end of the design. Don't put somewhere like in the beginning of the design. Like once you understand the whole design and like you see that these paths are like known timing violation path. So when I say that like known timing violation path, it doesn't mean that like there is a timing violation and you leave it. So especially we will be coming to that point. So we have something called CDC, right? So different clock domains. Let's say like I have higher clock frequency and another lower clock frequency. Whenever I want to interact between these two clock, right? So usually that also will be treated as a timing violation. But there are like some synchronization techniques where we can resolve that timing violation. So in such scenarios we will be putting those constraints, but I'll tell you like how to do that. But here the only methodology to solve the timing violation, the setup violation, is like one way is like reduce the clock frequency, other way is like to go for some kind of pipelining method, other part is you can go with some kind of uh, pipelining method or parallel architecture. Okay, any questions here? So this is the scenario, right? So you can see this is like where you can have a clock and you have this D that is slightly before the clock, right? So like for hold, now next thing is hold time. So hold time, now after the clock occurred, right? After the clock edge. So setup is somewhere like here it should be stable. And it doesn't mean that like as soon as you latch here, you can remove the input. So the data shouldn't go low here, right? So you have to hold this data for some time after the clock edge. We have to hold the data. Okay. So this is the time for setting up. That is why setup. So after this, we have to hold the data so that like your output will be stable after the clock edge, right? So this is also very important. In FPGA, we rarely see the hold violation because like whole architecture is fixed. But in case if you see, right, uh, uh, I mean, it is very tricky to handle the hold violation. I mean, it is not straightforward as such like in ASIC. So usually in ASIC, people say that like I am going to put some buffers, right? But here, one way what I can do is like I can go for some kind of strategies, synthesis strategies. So especially in the highly congested designs, right? So you start seeing the hold violation. because these flops, right, it is fixed. I mean, it is not you have designed. So this FPGA hold design is fixed. So in hold violation, either people will say that like I'm going to put the buffer at the clock path or at the data path. So that is not going to possible in the FPGA, right? I mean, like we have lookup table, the CLB architecture is fixed itself, so you will not be able to that easily you are able to solve, right? So usually you can go for synthesis strategies to solve this kind of hold violation. Okay. So what I was saying about the metastability is like in both the cases, hold violation or setup violation, what I'll be facing is metastability. So metastability is in the sense either I'll be like lacking it as 0 or 1. Okay. So it will be like the correct data will not be latched. Okay. So it is something like this. So whenever you have this data, let's say like this is the pattern of the data, like from 0 to high it is going. And uh, let's say like here, right? Here it is 0, here it is high. So you might, I mean, if you are like familiar with the digital logic, so you have some thresholds, right? So above this, it will treat as high. Below this, it will treat as low. But in between, if your clock latches the data, right, it is a metastability. Either it can declare it as high or low. Okay. In FPGA, even though in simulation you will see the high impedance or like undefined, but inside the digital logic I cannot have high impedance or like in between voltages. Okay, so theoretically we can say that like it is undefined or like metastability state, but it can be either go low or high, right? So basically like your whole architectural logic will go in these scenarios, right? So the main uh, impact of this setup and hold time is basically metastability. Okay, so basically you are spoiling your data. Okay, so another major issue is skew. Okay, so in your FPGA, so clocks are like not. I mean, flip flops are not like very near to each other. So as I yesterday we were discussing, so there are like lot of uh, switching matrix, and especially this clock doesn't go through the data path. There is separate clock path and data path. We usually say dedicated clock path. And one more mistake, what usually we do, uh, uh, like in FPGA design, uh, usually like how do we generate the clocks in FPGA? How we can generate the clock in FPGA? What is the source of clock for the FPGA? So it usually it will be like external clock will be there, usually PLL or MMCX or TCXO, especially like for a defense application, we go for temperature compensated oscillator, O1 compensated oscillator, OCXO we say, voltage compensated oscillator, VCXO we say. External clock will be there. From there we generate and get some base clock, let's say like 100 megahertz, 50 megahertz. But for my application, in usually in 5G application, we use some standard clock, which is multiple of the pre-clock. It will be like, I think, 122 point some value. So this clock we usually generate using PLL. And this whole clock, right, it will be through dedicated clock path. Okay. So we usually call it as global clock routings. But whenever I ask somebody to divide the clock, how do you divide the clock? We go for some kind of counter logic, right? So then that counter logic based clock we usually connect to our logics, right? So now what we have done, we are mixing the data path and clock path, right? So whatever the generated clocks are there, let's say counter based or any data based generated clock, that we shouldn't use as like in the sensitivity list. So what happens is like if you use that in the sensitivity list, like always at that generated clock, you're going to spoil the clock path, right? I mean, you're actually your data path is forwarded to clock path, and like you are messing up the thing. So you will see definitely when the design becomes congested, you start seeing the violation. So the lower end, like whatever the divided by clock you do using counter, so that you have to use it as a enable. Okay, you have to, your sensitivity list still would be running at maybe 100 megahertz to 100 megahertz. You have to make a condition that like always at positive edge of that higher clock, if this clock is high, and then perform certain operations. I'll show you that examples also how usually we do. Uh, so, and that will cause a lot of queues and critical path issues, and also don't use that data path clock in your actual clock. And now when the design is congested, your clock path also will have some. So usually that will be low latency path. Okay, inside the FPGA it will be low latency, but these clock skews occur especially in case of your a clock if it is coming from the external devices like inside the FPGA. One example I can give, like with my own practical experience. Uh, let's say like I have FPGA and I have one ADC. So I get the RF data from antenna. There will be a lot of mixer stages, all these things. And this analog to digital converter, like I'll get the digital data. Okay, bus of digital data. Now, usually we say source synchronous. This ADC itself will be giving one clock. Okay, so source will be same. I can say one MMCM will be there, or like I can say PLL crystal. So that clock will be going here, and same clock you're going to give to the FPGA also. So what this do, what this particular ADC does, it actually synchronizes this clock and this data, and it gives one clock. Okay, let's say this is the clock. But even though these two frequencies are same, there will be some skew in this path, and also here some delay, right? So this path and this path are like different. It is not low latency path here, mainly because these are like in the PCB. I mean, this is inside the FPGA, right? So these are depends on trace length. So because of that, you're going to get some kind of skew in the clock. Okay, skew in the clock. Okay, so these skews, how we can solve this kind of skews? Any idea? So it has to be, I mean, this queue has to be aligned properly, right? So this clock, I should know like how much skew is there. So basically this delay I know, right? What is the propagation delay of this particular trace? So usually by doing SI analysis by PCB engineers, so they will tell you that what is the trace length, what is the delay. So I have to avoid this queue also. How to do that? In the timing analysis, I have to say this Q value properly. Usually, there are some constraints called input delay, output delay. So using that, I can handle that. Okay. Yes. So you might have seen, I mean, one metastability issue is due to CDC also, right? Clock domain crossing. So you might have heard multiple times clock domain crossing, right? When do you say it is like two clocks are of different domains? What is the scenario? Clock domain crossing. Clock domain crossing also causes pickup and hold violation, right? So what is the scenario of clock domain? Have you heard about clock domain crossing? Yes. When do I say two clocks are like of not of same clock domain? Is it different frequency? Is it because of different frequency? If two clocks are of not of same frequency, do I say CDC? Is it the condition? Yes or no? Yeah, may be not of the same frequency. Okay. It's of not of the same frequency. Okay. So when I say clock domain crossing, it need not be like of different frequency. I can have CDC in the same clock frequency also. Okay. So when that same clock frequency issue occurs. So let's say like I have two PLLs, okay, two oscillators I can say, oscillator 1 and oscillator 2. So in this oscillator 1 and oscillator 2, these are independent oscillators, right? So it is of not of same, I mean, it can be like same frequency, F1 on, like let's say like F1 frequency, F1 frequency. These two are independent oscillators. So does it generate like phase aligned clock? These two, does it generate phase aligned clock? It doesn't generate the phase aligned clock, right? So if let's say like if this is starting at like uh, 0, okay, so this also doesn't start at 0, correct? So I can say there will be like maybe slight, at least, I mean, if there is coincidence and it starts together also, there will be picosecond or nanosecond difference, right? So I can say this way, right? Worst case, what will happen is same clock and 180-degree phase shift. Now your setup time, previously you used to get like, I mean, let's say you are latching one data, I mean, you are sending data flip-flop 1 at clock 1, CL1, and here flip-flop 2, you are basically sending it, latching at clock 2. Let's say this is CDC, right? I mean, different clock. So now if you are doing this CL2, okay, so here your setup actually like you are latching at this, so launching at this, so your actually setup analysis will become like half of that. I mean, previously it was uh, like just next to, I mean, like this, I mean, you had like complete T clock cycle, but here it will try to lag at T by 2 itself. Let's say this is like somewhere another clock domain, it is somewhere here. It will be complete mess, right? Like, I mean, you will get like very short duration, and if your data is not reached, so somewhere like you will just start messing up with the data. I mean, it will be complete mess, correct? So always like of different frequencies also is one CDC, but within the same frequency also you will see a metastability issue, correct? So this is also is considered as clock 1 and clock 2 from the different sources, okay? So from the different sources is considered as clock domain crossing. So now I said that like, I mean, from clock 1 to clock 2 I have to transmit the data, and this is the issue, correct? So what is the resolution for? What is the general resolution for this? This will cause the issue. I mean, if I'm like want to transmit a data from clock 1 to clock 2, same frequency, but it is of different domain. You can think like you have some external device also. You have one FPGA and you have another FPGA. And this FPGA is running one at clock 1. This FPGA is running at clock. FPGA to FPGA communication is also common case, right? Like in the complex design. So now we want to transmit this data. So both are running at same frequency. Now, do you directly take this data at this particular clock? No, it will cause metastability. So how do I handle this? Any methodologies have you heard in digital logics? Obvious methodology, what we follow is double clock synchronization. Okay, so double, triple, anything is possible, but as per MTBF analysis, usually we go, I mean, especially in the defense application, we go for higher clocks also. So generally we go for something like double clock synchronization. What we do, let's say from external asynchronous data is coming, right? D1. So at the receiving end, I can say CLK R receiving end. I will pass through two flip-flops of, then here this data out, right? So this data out I consider for my analysis. Okay, so this is the general methodology we usually call it as double clock synchronization. Okay, so this is based on metastability issue. I mean, MTBF analysis. So I mean, in here also, you cannot assure that like it is highly reliable. I mean, you can say here like 90. I say 99% reliable. Maybe when as you want to increase more and more reliability, you can go for triple flop, four flop synchronization, multi flop synchronization. But ideally, here I can say there is a more probability of data getting corrupted. But as you pass through another flip flop, so here it will be somewhat stable. So usually we call it as double flop. Any questions so far? Any questions so far? Hope what I'm trying to say you're getting, understanding. Great. So next thing, double flop synchronization for the same clock, it is fine. It is good. But let me consider one scenario. Here, like more than technicality, you have to think in terms of logical. So let me know like how it can be solved. I'll tell you one scenario, a practical scenario. I have clock. Okay, so this is the source clock, clock 1, and I have a data pulse here. Data pulse at source clock, DN clock, right? So now, if I want to uh, capture this, I have like this is the source clock. Okay, I have clock 2. Is this one. Okay, so this is clock 2. Now at the source clock, if I want to identify this, I mean from source clock to destination clock, I send the pulse to slower clock. So this I can say this is somewhere like 100 megahertz. This is somewhere at 10 megahertz. I want to transmit this pulse from clock 1 to clock 2. This is a CDC path. Again, this is also CDC path. So is it double clock synchronization is possible here? If I use double clock synchronization, what will happen here in this scenario? If I use double clock synchronization, what will happen? So this pulse, right? It is not even like single clock cycle, half clock cycle of this. So it will not detect it at all, right? So this will be missing. This is actually like whenever like positive edge I am seeing, so I don't see this pulse at all, correct? So logically, how I can resolve this? Logically, how I can resolve this? So on this we will be discussing more. Okay, I'll show you some RTL examples also. So, but like, can you just give me some idea how I can solve this? Hope
Participants
you.
are, sorry to interrupt you, sir. Participants are requested to answer the questions that sir is asking. You can unmute your mic and I think you should answer. Okay, sir, you can continue.
Yeah. So basically, here one way is like it has to be stretched, right? It has to be stretched till here. Correct? This is the one way, pulse stretching. So this is method one. We call it as pulse stretching. Okay. Another synchronizer, what we use called toggle synchronization. Okay. So when I say like I'm stretching this pulse till here, you will be able to see this particular pulse at the receiving clock, right? So this is one method. This is clear. But what is the disadvantage with this? So you should know like source and destination clock frequency. If you don't know source and destination clock frequency, this will fail. Another way, what I do
Sir, in the
is
real-time applications, sir, it will create the problem maybe, no, sir?
correct.
For
Actually, if you do not know the frequency of like source and destination clock, then it will create a problem, right? Pulse switching. So another way, what we go for is toggle synchronization. Toggle synchronization. In toggle synchronization, what we can do, like every edge of the clock, I mean every edge at the source, what I'll do, I keep toggling the signal pulse this way. I keep toggling. But again, if these pulse positions are very nearby compared to your destination clock, again that is also going to create problem. Okay. So third way, what I can do, I can go for some kind of pointer mechanism or counter mechanism. You know FIFO, right? In FIFO, how actually this pointer works? I mean, asynchronous, let's consider async FIFO. This is the third way of like synchronizing these scenarios. How we actually, so I mean, somebody asking to explain this pulse stretching. All the three logics I'll implement in Verilog. I'll show you that how it behaves. So async FIFO, how it behaves. So I mean, like, what are the signals in async FIFO? We'll have some write enable, correct? And write clock. And here in the destination side, I will have FIFO empty and FIFO full condition, correct? FIFO full condition. So the same logic, but here what I'll do, I'll not use some kind of what to say, data I'll not use. I'll use similar logic what I use for Python, like gray code synchronization between source and destination, everything I'll use. And whenever there is a pulse, I'll keep the pointer, like how many pulses I have received at the source domain. Then I will keep acknowledging that. Like I have received one pulse, second pulse, third pulse, I read third pulse, fourth pulse is third, fifth pulse is third. That is the more efficient, okay, highly efficient. But it depends on the application to application, which application you use in the real time. Let's say like I have data like this pulse. After this pulse is occurred, maybe after 1 second, I mean, I know that like it is not going to repeat. The pulse repetition rate is very important. At what rate the source pulses are repeating. I know that like 1 second, next 1 second, I'm not going to get any pulse. So in that scenario, I usually go for toggle synchronization or pulse stretching method. The pulse stretching method is not preferred as such. Pulse stretching method because like I don't know like source and destination clock many a time. So toggle synchronization is the ideal method what I usually use. Okay. So let me just quickly write this Verilog code, especially for simulation purpose, right? It is not always you need to go for Vivado, all these tools. So online tools are also available. Quickly you can simulate and show. Like in Vivado we had seen yesterday, right? The same way like the online tool also I'll just demonstrate so that like it will be helpful for you. Even like in your classes also if you want to demonstrate Verilog and all, right? So that is like simple tools are available in online. So one of the tool is EDA Playground. You might all know that. So let me just you can quickly you can parallelly try this also because this like you need not install anything. So without installation also you can test this tool. So edaplayground.com. So you just need to log in and you can simulate there. So let me quickly write the code. First, we will start with the double clock synchronization. This link also I will share so that like parallelly this code whatever I paste, right? So I mean I have kept all the codes ready because like for the I mean quickly I can like in 1 hour I can finish. We have 9 different synchronizers. So what I'll do I'll share these links in the chat so you can go through that whatever I explained parallelly you can implement. So first we will be going with we'll start with the 2 clock synchronizer. Like those who are new to Verilog, so I'll just quickly go through the code also, how we have implemented this, so that like you will get familiar. So here you can see, right? So you have like input, clock, destination, and this is particularly, I mean, it is not of the different clock. So async in is something like from other clock domain. I'm getting the data. So this is actually destination clock, what I'm getting, right? So here, uh, in the above scenario, I said that like clock 1 and clock 2, right? So whenever I'm going for the 2 clock synchronization, if you have seen that like I'm actually synchronizing with the destination clock. So I need clock 2 only, destination clock. So clock 2 as input I take. So you can see here destination clock. and also async in. This is the data signal. Okay, so here this is the clock, destination clock. So this is the data signal, and whatever synchronization I have, that is the output data. Okay, so here internally, what I have done, always at pause edge of the clock. So every non-blocking assignment is going to create one register, right? So sync flip flop one register is one flip flop. So here sync flip flop 1 I have assigned with async in. This is going to be created flip flop 1, correct? When I synthesize this, it is going to be created flip flop 1. So one assignment what you can try after this lab is please synthesize this whole design in Vivado or Quarter and see like how the circuit is going to be synthesized. And async flip flop 2 I have assigned with sync flip flop 2 assigned with sync flip flop 1. So this is going to create flip flop, correct? And finally, I'm assigning sync out with sync flip flop 2. Whether this one is going to create any register, is it going to create any register? Is this going to create any registers? This is just a wire, right? Assign statement is something like connecting a wire. So sync flip flop to wire, I'm connecting just to sync out. So it is a short, correct? So now test bench for this is, I'll write a simple test bench. And here, right, in the EDA playground, you also in the tools and simulators, you have to click on EP, open EP wave after run. And in this, you have to choose iCarrot simulator. This is for Verilog. I mean, most of the simulators are available if you want to run it in the model sim and all. If you give the institution email ID, so they will allow you to simulate all the simulators. You have this Cadence, Aldec, all the high-end simulators are available here. Okay. So as soon as you save and run, the link will be generated. That will be unique link. So this tool is especially useful for your teaching purpose. I mean, if you are like taking any Verilog class and all, so you can share this link to the students. I mean, I'll just share you also this link. So you can access, the students can access this code in the real time. Whatever you modify, they'll see that. Later point of time, they can experiment with this code and all. I mean, you need not share separate files. So in the test bench, what I have done, I have called this particular two clock synchronizer in my test bench, correct? So clock destination, I have generated local clock. You can see clock destination equals to not a clock destination, and which is of 5 time unit, right? So if this is in nanosecond, the total period is 10 nanosecond, it is going to generate 100 nanosecond clock, right? And one question I have, so if I generate this clock this way, right? Forever #5 clock destination equals to not of clock destination. Is it synthesizable code in the sense like whether I'm able to put this particular part in the FPGA? No, this is not a synthesizable code. This is just for the simulation purpose. Okay, so this particular point you have to be keep in mind. So like whatever we put it in the test bench, right? That is not synthesizable. Okay. So this is just for the simulation purpose. Whatever the delays we put, these are like not synthesizable. You cannot implement this in the FPGA. So this is just for the test only. Okay, I mean like it is like a just test platform. Will not be able to put this in FPGA. But in case if you want to generate this clock, then what is the methodology? You have to go for PLL, or you have to go you have to go for some kind of counter mechanism, right? So that will be synthesizable. But like #5, these kind of things are not synthesizable. You see, I mean, here I haven't put any print. Yeah, here there is a monitor and all. So these things are not synthesizable. I mean, you cannot synthesize and put it inside FPGA. This is just for test bench purpose. Okay. And once you save this, one thing you have to put here, because this is actually VCD dump based simulation. So you have to add the dump also. Okay, just to see the waveform. It is not straightforward like how you do it in Vivado. So you have to put some dumps. Okay, so let me just add the dump. I know I'm going little faster because like there are too much to cover in short duration, 2 hours. So timing is something like usually which I take at least 8 hours. So I mean there are like lot to cover in 2 hours. So but like I mean as much as possible, as much as simpler possible, I'll just try to cover. And I'll here basically I'm giving you all the pointers. I mean there are like now uh, if you are like not understanding any of the point, you have to just stop me and ask. So I'll be explaining. So this is the dump file. These two statements basically dump all the signals in real time. And this is for the simulation purpose. Okay. So now if I run this particular logic here, can you see the behavior? So you have async in, right? So clock destination is this, right? So like you can see, clock destinations falling edge itself, this clock in, I mean, the data in became high, right? But like destination, like I mean, the sync flip flop one, it lasts at the first clock edge, right? It's synchronized. And sync flip flop two, it lasts at the second clock, right? Final output is here, this. So you can see here, this is not complete clock cycle also. It is somewhere in the half, in between half clock cycle. I mean, these bits are varying, right? It is asynchronous signal. But if you see here, it properly aligned to the clock and it made synchronous. Everything is synchronous, right? So you can see here, it actually aligned everything to the synchronous, correct? Any questions here? Let me just pause for 2-3 minutes. If you have any questions, please let me know. Okay. So this is two clock synchronizer, right? So you have flip flop one, flip flop two, and you actually synchronize asynchronous thing, right? So now uh, we'll go for pulse stretching. Not pulse stretching, we'll go for the toggle synchronizer. Okay, pulse stretching is not popularly used. Uh, Let me show you toggle synchronizer. So here, even though this clock destination and toggle, I mean clock source is there, right? So here I need two clocks also in toggle synchronizer. Okay, input, wire, clock, source also I need. Okay, so then what I do is whatever the data, right? Like I can say it is source data, whatever the source data I get, with respect to that, I have to keep toggling one internal signal. Okay, toggle meta. So always at positive edge of the clock with respect to clock source. What I will do, uh, this toggle meta, I will make not of toggle meta with some condition. With what condition? With if source data. Okay, so I mean I draw this and show you like how exactly it is going to be implemented. So here what I did is I have source clock. This is the source clock. And I have one pulse here with respect to source clock. Whenever I see this data, right, with respect to source clock, just toggle data, right? Toggle data. I'm just toggling. Let's say if it is at 0. So at this point, I will make it high. And here at this point, I will make it low. So I keep making this particular thing. I mean, I'll keep toggling. So this is the funda of toggle synchronization. And the receiving it, at the receiving clock domain, I have to generate the pulse. Okay, out of this, I'll show you like how to generate the pulse. So this is the case, right? Toggle meta, I'll initialize with 0. So every source data, I will be toggling. Now, at the destination clock, right? What I have to do is, I'm XORing this. That too, not the direct XOR you have to do. So basically, at the destination clock, whatever toggle meta 2 is there, I have to delay by 1 clock cycle and then XOR. So can you tell me here in this is the source clock. Let's say the destination clock is this one. Okay. Here actually you have to one more synchronization you have to do. Two synchronizations. Toggle meta 1 and toggle meta 2. So toggle meta 1 and meta 2, because like locally also you have to, and the destination 2 clock should be there. And toggle meta 2, you have to assign with toggle meta 1. Okay. So now this toggle meta 1, right? So how it looks? So this is the clock destination clock. So whatever the data you get, so in toggle meta 1, you may see somewhere, I mean, if this is like slightly before this, let's say like slightly before this. So toggle meta 1 may synchronize this way, right? Toggle meta 1. This is toggle meta 1. Okay. One thing, sorry, here, let's not keep this far. I mean, this is actually, this will be so much confusing for you. So what I'll do, I'll try to simplify this whole thing. Let me just, let me make slightly more clock, okay? slightly more clock. Because if I put too slower clock, so another edge will not be able to see. That is one issue. Okay. So here, this is the destination clock. So then here, this you are going to identify, right? At this point, you will latch it and you keep latching. And let's say this part, this is exactly aligned with this destination clock. And you'll see this, right? This is the destination clock. Toggle meta 1. Meta 1. So toggle meta 2 is going to be 1 clock cycle delay, right? This way. Now, when I XOR, what is going to happen? Now, if I XOR, what is going to happen? Basically, if you see the logic, toggle meta 1 and toggle meta 2, I'm XORing. What is going to happen? So XOR is basically 0, 0, it is 0, right? So 0, 1 here, this way, and same way, going to generate this pulse. And these pulses, XOR is like 1, 0, XOR, I mean 1, 1 again, it will be 0, and this is 1 pulse, correct? So irrespective of like what is the frequency, so this pulse is actually width is at the destination flow, correct? So this is the usage of toggle meta synchronous, I mean toggle synchronous. So again, if these pulses are very far, then only it can be used. I mean, if you get burst of pulses, right? So then like you have to go for FIFO kind of synchronized. Okay. So now let me just simulate this. So I generate two different clocks. You can see a source clock, which is of 125 megahertz, destination clock slightly lower, 100 megahertz. Okay. Then basically source data I kept on changing. Okay, like only one pulse I just to show you that like how this toggle synchronous. Okay, I mean like I can add some more pulses. Also. We'll see that like how it works. So this link also I'll put it in the chat so that like you can experiment from your end also. And somebody asked like what is the use of dump file? So ideally this simulator works on GTK waveform. I mean for waveform viewing, it uses in the background it uses GTK waveform. So for that requires a VCD file. VCD file is like dump of all the samples whenever it simulates. Whenever I'm simulating using iCarus, it dumps all the samples, like each time stamp, how the signal behaves. And that dump will be plotted using GTK waveform. So for that, I have to write this dump file. So dump file has this waveform. So iCarus itself, it cannot generate the wave. So it uses some external software, GTK wave. See, this is the source data. And in the toggle destination, okay, so this identified this toggle method. So then, one second. Source data, toggle destination is the output, final output, right? So right. So you have source data. So this is the pulse. Okay. So that I have synchronized with the local clock, right? Toggle meta, source data I have synchronized. Then there is actually toggle data, right? Like, just show you the logic parallelly. Correct. Toggle meta. So toggle meta is whenever there is a data, I'm actually toggling it, but it source correct. So if there is data at positive edge of the clock, it's just synchronizing. Okay, some issue with that. So one more thing, one important thing here also, right? This source data was edge of the clock. Okay, source data I made it high. So if there is source data, I will toggle. Okay, so let me just synchronize this. I mean, so usually in the test bench, right? So there will be some delta delays also. Let me just try synchronizing. So I mean, it was not expecting as expected. It is not behaving that way. Let me just create one source meta and try source data meta. like that is not updating. I'll just confirm you this part. I mean, basically the logic is correct. So I mean, somewhere in the simulation it is going bad. So I'll just confirm you this part. I mean, maybe tomorrow or like I'll just mail this regarding this part. Okay. So ideally, like you have to toggle this, and whenever you actually toggle, after you toggle, that you have to detect at the source domain. So that is the whole idea behind. Okay. So then finally in the source destination, you have to basically XOR that. Like, I mean, it is ideally, this is the logic behind. Whenever you XOR the whole thing, so you're going to get the pulses at the destination. Okay. So somewhere the simulation, I mean, you can just, you have the code like I have shared, right? So you can try simulating in the Vivado also. So ideally it should get this. I mean, I'm not sure like whether any synchronization issues are happening. I'm not sure. Let me just check and get back to you in the tomorrow session. So apart from that, so we also have one is actually asynchronous FIFO, right? So in the asynchronous FIFO, it is for data. I mean, when you have multi-bit data, right? So like what happens if you actually like one bit synchronizer we have so far discussed, but is it same case for your data also? Like let's say like you have 64-bit data or 128-bit data. Is it possible to implement similar scenario in that case also? I mean, can I go for flip-flop based synchronization? What will happen if I go for data? In data, what is the issue you will face? There will be skew, right? I mean, you cannot go with some kind of flop based synchronization, correct? So because like let's say like I have 16-bit of data, and if I implement all these kind of synchronizer for 16-bit of data, so there will be like in case of placement and routing, all the flip flops may placed in like different locations, right? So that will be like not possible. I mean, like especially like that will be creating lot of queue and like data corruption. So for that, usually what we do is like I have one FIFO, and in FIFO, I have to keep writing the data at source clock, and I have to read the data at destination. Okay. So here you can actually like go for this kind of synchronization, especially for different clock. I mean, like when you want to read at like one clock, and if you want to write at different clock, then you go for FIFO kind of synchronization. So how do you calculate this depth of this FIFO? I mean, how to actually come up with the depth of this FIFO? So usually we go for something like, I mean, whether like, let's say like this is running at high speed, let's say 100 megahertz, and I'm reading at lower speed, 50 megahertz. Can I keep writing the FIFO? I mean, is it possible? I mean, every clock cycle, can I get the data? If I'm writing at 100 megahertz, reading at 50 megahertz, so is it possible to keep writing the data? No, right? So there will be like only in the FIFO, even though like I have like in between these synchronizer, so there will be burst transfer. Okay. Also, usually we control this flow of data, right, using FIFO full and FIFO empty. FIFO full and FIFO empty. Okay. So whenever this like in the 100 megahertz domain, I keep writing the data. Okay. Then this FIFO full will say that like, I mean, now the data is full. Based on that, this can stop the data. Okay, in the source domain. Same way, whenever I am like seeing the FIFO empty flag, right? So I can actually stop reading the data. Okay, I mean I'll see that like whether there is a data. If FIFO empty is not high, right? So that then it means there is a data in the file. Then I keep reading the data. Okay. In certain cases, what I do, like let's say like I keep writing the data, burst of data at 100 megahertz. Some 50 data I write at 100 megahertz. Okay. Then I will have some 20 microsecond delay. Then again some 50 data I write. So I keep going with this kind of sequence, right? So in that scenarios, what we do is like we have to see that like what is the worst case scenario. Like let's say 20 microsecond, I don't write anything, and 50 data I write together, and so 50 data and 50 data I write together. So total 100 data I have written in 100 megahertz. After that, I will have 20 microsecond and 20 microsecond. Total 40 microsecond delay I will have. So 40 microsecond delay plus 100 data. So total how much clock cycle it takes. According to that, whatever the read domain is there, right? As per that, I have to understand or identify what should be the width of my, what should be the depth of my book. Okay. So that is a general scenario what I do. I mean, there are like a lot of things and documentations available on this 5 to 10. So, I mean, I'll not go in detail on this part. Okay. So, one more thing, what I missed, one more logic what I missed in case of synchronizer. So let's say like I have one clock and I have signal like this, asynchronous system. And I have to identify the positive edge of this. So what is the logic generally we use? What is the logic used for identifying the positive edge of the data? So these are three important things in synchronization. Actually, one is toggle synchronization, where you keep identifying the toggling part, that is using XOR, because it identifies positive edge or negative edge. It basically toggles, it generates the pulse. But in many cases, we may have to either detect only positive edge. In many cases, either we may have to only detect the negative edge. In that scenario, what circuitry we use? So basically, we have to delay this. Like first, we have to synchronize using one flip flop, one clock cycle, and in another clock cycle you have to delay. So now what operation do I need to perform between A and B to generate one pulse? Wherever positive edge is there, I have to generate one pulse. So now what operation I have to perform? I need to get this pulse. It is A and not B, right? That will identify the positive edge. Wherever the positive edges are there, I can identify in the data. So this positive edge detection also is like one of the, I mean, most of the time you will be seeing in your FPGA based designs. Okay. So same way, you may have to detect the negative edge also. So similar conditions, but like what modifications I have to do? What is the condition for detecting the negative edge in flip flop? So you have to again delay, right? Same way, two times. So here what operation you have to do? It is not A and B, right? So reverse operation. Okay. So this is actually positive and negative edge detection circuitry what you have to use in your design. Very important. Okay. So these are the some of the synchronizers like async 5 we discussed. And in many cases, vendor itself will give you the CDC bridges. So this is especially in the ASIC. Okay. So when you go for the ASIC kind of application, you go for vendor-based CDC bridges. Okay. So now we will see various constraints what you have to give it in Vivado or Quartus. Okay. So let me open my tool. Vivado I'll open. So I'll show you like how to add the constraints. By the time the tool opens, I'll just briefly tell what are the different constraints we have. So one is like create clock. So let's say you have you have a scenario from external, you are getting 100 megahertz clock to FPGA. Now, whether tool know what is the frequency of this when in the Vivado or like Quartus, whether it knows that like what is the frequency of this external clock? No, right? So what we have to do, like we are actually informing the tool that what is the frequency of this external clock. That is basically we use something called create clock constraint. Okay. In the create clock constraint, we also inform the tool what is the frequency of the external clock we are getting and what is the duty cycle, what is the skew. All this information, right, we will be mentioning in create clock constraint. So it is not, I mean, whenever I say I'm giving a create clock constraint, FPGA is not going to create some clock as such. It is just like for the timing analyzer, you know that like in the initially I have shown you that like how to calculate the setup and hold violation, right? So in setup and hold violation, when I have shown you, so it requires the period of the clock, right? Many times that is also one of the mistakes what we do. Like I mean, we run the timing analyzer. You don't see any of the timing violation at all. Mainly because you haven't given any constraint. Yesterday in Portals, I was showing you some of the uh, uh, timing related reports. In that, it was showing one warning. I mean, there was no negative slide, but it was showing warning saying that like there is like lot of unconstrained path. So unless you constrain the path, you give the information to the tool that like these are the timing constraints what I have. So it doesn't analyze any path. It says that like I mean all the timings are met. I mean because for the given constraint for given information, it might have analyzed whole path. Okay. For that reason, it is very important to give the timing constraint. Okay. And create clock is something like as I mentioned. So it is basically creating the, I mean, you are saying the external clock. What is the frequency of external clock? And you have something called generated clock. I mean, if you see the second constraint, if you see the second constraint, generated clock. Generated clocks are nothing but these are basically like internally in FPGA itself, you are generating various clocks, right? Maybe using counters, maybe using PLLs. So those clocks you tell the tool. I mean, especially if you are generating clocks using PLLs, you need not say the tool that like what is the generated clock. Okay. And you can give what is the clock latency, same way like what is the clock transition. and clock getting checked. And in clock groups, especially, so when you have basically like multiple clocks, right? Let's say like which are generated from the different sources, like 20, 30 different sources in larger designs, right? In Samsung, when I was working, so like we used to work in like larger base station design where we have like 4 to 5 FPGAs and like multiple clocks, multiple peripherals. So we have to identify which are the sources where actually like this clock uh, I mean, what are the base clocks and which are the group clocks? All these things we have to group it. So that we have to say that like what are the clock groups which are from the same source, so that like it helps in the timing analysis. So input and output delay, as I mentioned, like it is like from the external source. Like let's say you have external device, from that point to inside the FPGA, how much delay you have, right? Like I mean, uh, let's say you have external ADC or some other component. So you are connecting to FPGA from this component to FPGA. Let's say like you have 2 nanosecond delay, right? Bus delay. So that we give it using input delay. So these are all actually we are giving for your timing analysis. Okay. So same way output delay, like how much it takes. And one more thing, like whenever you have external ICs, right? Like let's say ADC or some clock, external clock outside the FPGA. You also for setup analysis, right? You also see that data sheet. In the data sheet, they will be giving like what is the setup time of that particular device, what is the delay internally it is giving, like clock to data delay. All this data you have to put it in the timing, I mean, especially in this particular constraint. So that will help for the timing analysis. Basically, we are giving the information to the timing analysis tool. That's it. Okay. So architecturally, we have to resolve using the synchronizer, what we discussed, like multi-clock. I mean, few of the synchronizers we discussed, right? Uh, One is like toggle synchronization, FIFO-based synchronization. Using that methodology, we have to resolve. But if you want to analyze all the after designing all the synchronizers, architecting properly. Still, if you are seeing some timing violation, then it might be due to the no proper information given to the tool itself. I mean, especially few people will misgiving this clock data, or whenever like we go for this kind of synchronization. So we have to constrain that as a false path or multi-cycle. So many people will miss that constraining that path. So uh, we have to actually careful about constraining the data. Okay. With respect to tool, how you can constrain it. So here, right, if you source in the sources, you have something called constraint. So if you right click and if you go to add sources, here you have create constraint option and create file, and you can say test.txt and finish. So this is one way like you can add the constraint file. Then, I mean, after actually adding this constraint file also, one thing you can manually add these constraints. Apart from that, post implementation, right? Like let me run this implementation of this design. So I think, do I have any design here? Yes, I have, right? So after that, so basically here you'll get an option to add the timing constraint. So you have a GUI where you can add the constraints. Like if you, like let's say create clock, all these things, right? You have a GUI where you can directly say that like what is the frequency of that clock. Let me just show you that as well. So today I may not be able to show you that design with the setup violation. Tomorrow it is actually debug session, right? I mean, I'll be explaining you debug IPs and also that doesn't take more than one and a half hour. So like initially I will continue with that whole thing with the timing itself tomorrow. Maybe first half an hour I'll continue with the timing. Then we will start with the ILA IPs, debug IPs. That way we will plan.
Sir, FPGAs, they have DLL, delay lock loop, correct, no, sir? So anything we will be able to give some constraints for those using these?
Delay lock loop, the PLLs actually, MMCMs or the PLLs, right? Multi-mode clock generators.
Yes, sir.
Yes.
For those,
So correct. So whenever you actually add the IPs, right? So you need not give the constraint because as such IPs, tool knows that like what is the constraint for it, right? So usually like if you generate any clock, then you need to say that like this is the generated clock. So ideally these constraints are something like we are basically saying the tool that like whichever the information it doesn't know. But in the let's say like you are instantiating one PLL, all the informations are there in the PLL itself, like what frequency you are generating, what is the jitter of it, everything it knows. Tool already knows. So in case of PLL, you need not be constraint at all.
Cool.
So you can avoid giving the constraint for PLL because tool already know that that PLL IP itself we create using tool, right? So you need not give any constraint. But let's say like you have designed your own DLL, right? Which tool doesn't know, like what are the frequencies and like what are the jitters. In that scenario, you have to give that any logic, custom logic, whatever you write. So by the time it implements, I mean, it takes another, maybe like another 2-3 minutes. So if you have any questions, please let me know. I know I was little fast because like too much to cover in short duration. That is that. Any questions? Okay, let it synthesize. I'll just show you that methodology, how you can add constraints using after implementation. I was expecting more questions from this crowd because, especially in my BITS work integrated learning program, uh, I mean, all are working professional, around 200 plus crowds will be there in each batch. So as soon as I pause, I mean, people will be waiting for questions. I mean, mostly working professional, and I was expecting from the professors crowd also similar thing. So please let me know if you have any questions. So I'm happy to answer this. So if you want to give constraint here itself, XDC itself, that standard syntax will be there. So you can search something like Xilinx design constraint guide. Same way you will get Altera design constraint file. So you'll get a syntax. So maybe for this create clock constraint also, I'll just show you the syntax.
Excuse me, sir.
Yeah.
Sir, suppose if we have to implement a code that belongs to some emerging devices, maybe FinFET, tunnel FET like that. So which kit is suitable for the same?
You want to design what actually?
Sir, some circuit based on emerging devices such as FinFET, tunnel FET like that.
No. So actually, these are analog part, right? So those things
Yes,
we
sir.
cannot implement on the FPGA side. I mean, FPGA is something like whenever you have some digital applications, right? Like let's say like some communication system, or let's say crypto, or if you want to experiment anything related to quantum. So those circuits you can implement. So those are analog things you cannot actually. These are actually on top of that, right? This whole FPGA is built on top of FinFET itself. So this is a FinFET technology. So those things we cannot implement on the analog side, we cannot implement on the FPGA.
Okay, sir.
Only purely digital aspect of it, like we can implement anything if you want to
Sir,
experiment the digital
yes,
thing.
sir. Sir,
Yeah.
actually we implement some circuit and do simulation based on FinFET devices and some more devices are there. So actually circuit implementation is there. So I think we can convert such type of devices in the form of circuit and then we can implement it. Maybe I am
Those
wrong.
are yeah, those are analog. We cannot implement. I mean, like if you are
Hmm.
actually you might be simulating in some PSpice or cadence, right? So those things.
Sir.
So those things we cannot do. So anything which can be kind of RTL or Verilog, it's a digital design, especially digital design. We can put it here.
Okay, sir.
Let's say like you are testing some kind of memories, like where SRAM things and all. Those are like memory models you have to create. I mean, let's say like analog also equivalent digital model you have to create and put it and test it, because here everything boiled down to lookup table, right? So that lookup table mapping we have to properly think, because analog circuits we cannot map into lookup table like at the end, right? So that is the issue. We cannot put that.
Okay, so sir, any memory that is based on CMOS logic, we can implement.
Anything on the digital or yes, digital
Uh,
side.
yes, sir.
Yes, yes.
Okay, sir. Okay, sir. Thank you.
Thank you.
Sir, is there any relation between timing delay reduction and the power consumption of the CMOS logic circuits?
Yes, yes, yes. So, I mean, like, this all interrelated, right? So, whenever you say that, like, you are reducing speed, so your power consumption is also reduces, right? I mean, basically, your power consumption is also depends on like how much transitions are happening, frequency, right? So, it's interdependent. I mean, it's all actually what you can say, area, power, and time. These are all interdependent. It's not like independent variables. If you actually try to compromise one thing, and another thing also be compromised, or like it will be improved. Let's say like you are going for more area, uh, like you might actually compromise in terms of like, more area will actually help you to achieve higher speed, because like you can go for higher parallel paths. But let's say like you are going for smaller area, then what happens is like your critical path, all this will come into picture, and like you cannot do some parallel processing. You have to basically go with like one after another sequential. So recently, a year back, I have filed one patent in terms of one smart antenna device. So in that, like what we had done is like whole processing, right? I mean, the antenna array processing, we had actually reduced the timing. So that was the trade-off there. What ideally, like this antenna processing will be done clock after the clock. I mean, basically, if you see 256 array antenna, so the processing time is too high. So what we did is like we went for area compromisation. Like we implemented everything in parallel, and within short time, like whole 3D array can be calculated. That kind of implementation we had done. So it is again like a kind of area. Whenever you compromise this area, you can achieve a lot of high speed things. But like when you actually try to reduce the area, you have a limited lookup table. So with the limited resource, you have to reuse, keep reusing again and again. So that compromisations will start happening. So it's all interrelated.
Okay, sir. Thank you.
Any other doubts from the participants?
One last thing I would like to show, like this routing complete. So then I'll just show you that how you can add these constraints using tool. Then maybe like we can quickly wind up.
Okay, sir.
Meanwhile, I'll also share the feedback. So please, I mean, yesterday I got few feedback that you need to understand some of the concepts. So I'll try to include that concepts in the last session. Same way, if you have any concepts to be learned, right? So that one thing is like partial reconfiguration concept. So I'll include that in the last session. Same way, like if you want to learn anything specific, that would be really helpful for us to update. I mean, because we have 2 more sessions, so that we can incorporate those things in our session. So please fill. I mean, yesterday I got only 10 response. So please do fill everyone, so that like we'll get some idea like what to cover and like whether you are really understanding what we are teaching. So quickly, I'll share you the feedback link also. I have shared the link in chat. Please do feel that like what we could improve and what are the new things if you want to include in the next 2 sessions, right? So anything related to FPGA we can add. Yes. So one thing like I was telling you about here we can add the timing constraint. So if you see here, so basically here we have option called constraint wizard, right? If you click on the constraint wizard, so here it will initially read the netlist and it will say that which are the pins are available for constraints, adding the constraints. So you can add those constraints. So, I mean, whenever you run these devices in the server, it will be faster. So if you run it in local PCs, so like even 32 GB is not sufficient. I mean, because it requires a lot of parallel processing and all. These tools take a lot of time. So you can see, right? Like, I mean, right now I haven't added any constraint. So it is showing worst case negative slack is infinity. So ideally, we think that like there is no negative slack. I mean, even if I have the timing violations, I think that there is no timing issue. So you can see here, like you have to see that like test XTC is my file. Click OK. then it will start adding the constraint. It will ask like what constraint do I need to add, right? So now if I go to constraint wizard, click next. So it will ask to add various constraints. So right now, you are not seeing any pins because whatever the designs I have created, that is a purely combinational design. Let's say like in your design, you have added one clock signal, input clock, right? So, or like you have added a flip flop, right? So all these things will be listed here. So directly you can assign saying that that is the frequency of that clock is this much. Okay, so that way you can actually create input delay, output delay, everything you can put it here. Okay, so that is the thing what you can do it using this constraint. That is that's what I wanted to convey. Anything else? If you have, you can let me know. Else, we will discuss tomorrow. Thank you. Please do fill that feedback form. That will be really helpful for us to improve the content as well as plans. Thank you.
Thank you so much, sir, for this wonderful session and the informative session. Hope it will be helpful for the participants.